Hello, everyone. Welcome to another Rootlabs at lunch organized by DataRoots. These events are being organized by the Machine Learning Guild, which is the research lab for machine learning within our organization. Today, we've got a wonderful guest, Hans. And Hans will give us an introduction to hyperparameter tuning. He will outline several methods that you can use to perform this, to improve your machine learning models. And at the end, he will compare them as well in a demo. We've put a poll out, so before watching this presentation, might be worth answering the poll to see where your thoughts are at when doing hyperparameter tuning, or if you do it at all. All right, that's all for me now. Hans, the floor is yours.
Okay, thank you very much. Let me quickly share my screen. Okay, so a quick overview of what I'm going to present today is basically what is hyperparameter optimization, what is it, why do we need it? I will give a comprehensive overview of some algorithms that are out there that are aimed at making our life easy, and indeed compare them using a quick demo. So first, hyperparameter optimization. What is it? Basically, when we build a machine learning model, when we train it, we have both parameters and hyperparameters. Parameters are trainable by the algorithm. Think about it as the weights we assign on every edge, where to split our decision tree, the weights of all the edges of our neural network. Those can all be trained by data and give us the right predictions in the end. Hyperparameters are, by definition, untrainable by the algorithm, and they are just used to define the model architecture. Think about it as the number of levels in a tree, the number of trees you combine in a boosting algorithm or in a random forest, the number of layers and nodes you use in a neural network, or even your activation function, your distribution that you try to fit. All these define the model architecture, how the model looks like, and what your machine learning model is actually going to do. They also control the learning process. Think about it as which optimizer are we going to use, what kind of learning rate do you use, is there dropout, how big is the dropout, how do you penalize weights in a tree model. All of these just define how your model looks like. It doesn't define which predictions you get in the end. Now, why would we optimize this? Well, both to increase performance of our model. If we tweak the right hyperparameters, we might end up with a much better model, which is much more specific and can give us much more better predictions. It also increases the reproducibility of our model. If we build a tool to tune our hyperparameters, it can be reused. If we use the same seed, it is reproducible and we will end up with the same model all the time. And it saves time in development. If you can build a tool, you can automate it, and you don't have to look through all the different trials or all the different, or you have to try less, tweaking your hyperparameters by hand. Now, why don't we? Well, because it is hard. The validation loss is usually non-concave. It can go very convex, so it doesn't always lead to a nice optimum all over the surface. It's usually non-differentiable because not all of them are continuous. It sometimes gives very nice edges and corners in there. We use mixed input. We can use categorical hyperparameters, both categorical and continuous. So it's by definition hard to optimize, and it's almost always expensive to evaluate, because every time we try a new setting of hyperparameters, new set of hyperparameters, we have to train the machine learning model all over again, which can take a long time before you get your results. Now, to show you something on how it might look and why it's usually non-concave, just think about this graph as your response surface, or basically the surface over which you have to find the optimum. Well, if you start looking here, and if I turn this right, if you start looking here, you will probably end up somewhere here, because here you leap into edges and you don't know where to start to end up here at the red optimum if you want to maximize all of this. So all these edges, all these non-concave non-concavity, non-differentiability, because you have straight edges here, makes our life difficult if we want to end up here. We should start somewhere already very close to it to reach the optimum. So it's much better, or it's much more advisable, that we try to find a tool to do this for us. Now, for that, we need an algorithm. So we want to optimize a loss function over a graph structure configuration space. The configuration space is basically all the different sets of hyperparameters you can choose. You optimize both of discrete, ordinal, continuous variables, which are your hyperparameters. And you also have to choose which hyperparameters to tweak. Some are more important and have a bigger impact on your model performance than others. So we want to use an algorithm to learn good values for those hyperparameters. How do we do that, and what do we need from such an algorithm? Well, I like to say it is a fresh approach, and fresh stands for flexible, robust, efficient, scalable, and helpful. Basically flexible in terms of its configurations. You want to add both discrete and continuous hyperparameters. It should be very, very extendable in that sense. It is robust in its application to various problems, model architecture, so it should both work for tree learners, random forests. It should also work for neural networks. It should work for a mere nearest neighbor algorithm. Whatever, it should be robust and applicable to various problems. Also, you want it to be efficient in its performance. You want to find good hyperparameters quickly, very fast. And you want to find good hyperparameters, not just a fast and that ends up somewhere in a sub-optimum. You want to have a very performant algorithm. It should also be scalable in runtime. So you want to distribute it across computing nodes to make it much faster. And it should be helpful, which means that you need, in Python at least, you need a maintained open source solution, which is accessible for free. So you can actually use that. I found one for you. That's for the demo later. Now, if you want to look at a few hyperparameter optimization algorithms, I found 4 different types. First is a no-look approach. There are model-free algorithms, model-based algorithms, like our beloved Bayesian optimization, and something of everything, like hybrid models that can even surpass the previous 3. Now, I will quickly glance over a lot of them and just give you some insights on what these algorithms do and how they can be used. First one is the no-look approach. Basically, you can decide not to do hyperparameter tuning at all. You just use the vanilla models, which might perform reasonably well in general and only sometimes, because you might very easily find settings in which the vanilla models perform not that well. And then you're stuck if you don't want to go into hyperparameter tuning. Or you do manual selection of the hyperparameters just based on gut feel, previous experience. We know an algorithmic approach is probably better, but if you have some experience, you can use those hyperparameters. Or as Dan Ryan said in his presentation, you can use a graduate student descent. Like, it's a very popular tool in academia, where you have a small army of grad students, and you just give them a set of hyperparameters and let them play around with it. And then you decide which one comes out best and use that one. So the no-look approach, no hyperparameter tuning or barely any hyperparameter tuning or manual work is probably not going to be the best. We can better use an algorithm for that. There are some model-free algorithms we all know of, our beloved grid search, which is an exhaustive search over a grid of hyperparameters. I will quickly use my pointer here. You know that it goes full factorial. So whenever all different choices of each hyperparameter you can try out, or you can just pick some on a grid, which is easy to see on this graph. You will evaluate for an unimportant parameter twice as much configurations, which will just end up in exactly the same performance because this was an unimportant parameter. We could have pruned that one or not try out different configurations on that one because it's unimportant. It gives you the same performance. And on your important parameter, you might just miss by accident the optimum. You might come close to it, but also there's a big chance you are not close to it at all. For that, random search is a lot better because instead of looking at the grid, it just throws all your different hyperparameter settings or your configurations into this box at random, and exhaustively searches through them, which might mean that you can actually, by luck, come up with the most optimal hyperparameter. Now, in this setting, when there is an unimportant one and one important one, you might be lucky. If you have two important ones, you see, and excuse me for my bad paint skills here, you might see that you actually end up in a suboptimal anyway, because if you pick this one, gives you the best performance on this parameter. If you end up in this configuration, you might go for the other parameter, whereas the optimum is probably somewhere here on the edge, which you at random didn't try out, so you will not end up in the optimum anyway. Or you can use evolutionary search. That's a little more well thought through approach. First one is like just using heuristics, like the particle swarm optimization. Is basically doing follow the leader. From your first hyperparameter configuration, you decide to go in the same direction, so search in one direction, which you choose at random. And then after every iteration, you can see like, okay, what was the global best? What is your personal best that is on your path? And decide your new motion in which you search. Think about it again as in this grid. You just decide to move towards each other, and you might end up on this setting by moving your iteratively in this direction and this one in that direction, and then end up with the optimum. So that's basically what particle swarm optimization does. Follow the leader, follow the best one you have seen so far, and evolve in that direction. Or you can use a genetic algorithm, which is basically from a more Darwinist perspective. You can go from parent offspring. So you have a set of hyperparameters, and then you decide to combine them. So you go from parent to offspring, and your offspring is your new configuration to test based on three principles. Elitism, so you keep the best part of the best solution. So by combining both, you can see that some hyperparameters are in common, and you will keep those. Then you cross over, so you swap subsets of those which are not at the optimum yet, and then you mutate it. You might, like in a Wolverine style, you might grow some claws from your hands. You apply random changes to become at a more optimal solution. So you just apply that randomly and hope to, with some noise, end up at the optimum. You can also go a little further than that, and it's a covariance matrix adaptation. It's also an evolutionary strategy, which basically, instead of just mutating at random, mutating in a certain direction. So this takes into account the covariance between hyperparameters. So some may depend on each other. Just think about the depth of a tree and the number of leaves in a tree. There are probably high correlation between those. This will make use of that fact or that observation to evolve in a similar direction for both by adapting your covariance. So if your covariance matrix is very round, it doesn't really matter. If they are, like here on the right, if they are highly correlated, it will drive the direction, or it will inform the direction in which you can search better. And you can add steroids. That's a fourth option for the model 3 algorithm. And what I mean with steroids is basically successive halving. You don't have to keep working out or keep trying out a configuration that is lowly performing or does not perform the best. So you assign a budget, you try some different configurations, and then after you try them, you decide to drop half of them, or you drop a quarter of them, or you keep only quarter of them. That's based on your preference or on how quickly you want to proceed. And you drop those configurations and assign a bigger budget in the next loop to those who are left over. What do I mean with the budget? It can be samples, so the number of observations you use to train the model, the number of epochs, or just time, cron time. You just train it for a longer time on those that are most promising. And that way you keep iterating until one configuration remains, and that will be your optimum. So it works like this, like after a while, your full budget, you drop half of them, then you continue training these for more, and with more budget, you drop half of them. Here you are left with 2, you drop half of them, and this is the one that you train for the full budget, or you train for the remainder time you have left over in your hyperparameter tuning exercise, which is basically the one that minimizes your loss. Hyperbend is another type of successive halving, but it tries it multiple times. So it adds an outer loop. It does a grid search of the number of configs you try and the minimum amount of resources that you add per config, which basically means, like, what we saw is that successive halving depends a lot on what are the starting configurations you're trying. Now you can try to find multiple sets and run the successive halving, so this inner loop, over it repeatedly and end up with a better solution than trying it just once. So that's what Hyperbend does. What we see from the model-free algorithms is basically they are flexible, they are robust, scalable, and helpful. So you have some packages for them, but they're highly inefficient. So it doesn't guarantee that you have the best hyperparameters, because you just start always from a random set. You just sample from your parameter space, you try those out, and within that set, you decide which one is the best and try to evolve toward a better one. So it does not learn from the past. Okay, evolutionary research does it a little, but still it just points you in a direction. It doesn't say, like, how far should we go? How much can we learn from what we've tried before? That's where model-based algorithms come in. It's basically sequential model-based optimization, SMBO, that you see sometimes pop up in the literature, and it's Bayesian optimization. What does it do and how does it work? It basically defines a surrogate model. And a surrogate model is basically a model that is way easier to evaluate and to optimize. And it just maps your configuration space, so all your choices of hyperparameters, to your loss, your validation loss, which is meant to approximate the test set loss, and it has some uncertainty. So it very elegantly introduces some uncertainty. We know that we're not there yet after doing it once, but you can build a model, and you can build a better model using more trials from your configuration space to really map it to the loss. And then you have your acquisition function. So you have a surrogate model trying to mimic what your outcome will be given a certain trial. Then how do we proceed to the next? That is what your acquisition function does. So it helps you choose the next configuration to evaluate, which is more informative to build your surrogate model up, or points really in the right direction, like this is where the optimum is most likely. And here is where you introduce the trade-off between exploitation and exploration. Exploitation, you try to look at the full of the full parameter space, hyperparameter space, and try to explore new areas. And exploitation is then trying to really build on the knowledge we already have, what is the most optimum already, and try to mimic in that neighborhood to find if it's indeed the optimum. A very often used acquisition function, and most of the tools use this, is the expected improvement, which is basically the expected value of how much better the next result will be compared to the best result we have obtained so far. So maximizing that, or trying to find the maximum of that, is really giving you the next parameter a configuration to try, given that it's going to be, is most promising to be better than what we already had. Different choices of surrogate models, and you might have seen pop them up, is a Gaussian process, the GP model, which basically build a Gaussian process to mimic your true objective function. Random forest, which is then the SMAC approach, Bayesian neural networks, you can't think about it, it exists, and the 3-parsen estimator. Let me quickly go through them, and it will give you more intuition on what we are actually doing and how it works. The first one is the Gaussian process. Gaussian processes are closed form available, and the uncertainty is nicely built in. Like the full line is here your Gaussian process formula. The dotted line is your true objective function. And you see that the minimum is clearly here. We just try some observations. So we try some hyperparameter configurations. And we build here the straight line with an uncertainty interval, which is clearly a Gaussian overlaid between those points. And then we can see, okay, what is our best point now? That's here, the orange line. And then we build our acquisition function, which is basically all the area below this line and then made negative. And then we choose here the maximum, which is your acquisition max. Here is where we are going to try our new parameters, configuration. And we go to the next step, which is basically we have this new observation. We have evaluated the function. We have built a model for this and see how well it performs, which informs you on how we can build a surrogate model. So the straight line here looks already a lot different. The uncertainty also goes down, especially between those points, you know, like, hey, here was our evaluation. In between, there's less certainty of our model. So it will probably be very close to the real one. Then we built our acquisition function again, based on a new line. We come up with this, and here's our new trial. And that way we have evaluated. So here we evaluated it twice. Here we evaluated it thrice. We build a new evaluation here, and we update a surrogate model, and it clearly finds now this hyperparameter configuration, which is very close to the minimum here. So that's how it iteratively builds, including uncertainty, how it builds our model and how it finds the optimum. Of course, Gaussian processes are far less flexible for categorical hyperparameters. Gaussian is very easily fitted on. It is a continuous distribution. So for all categorical hyperparameters, this one doesn't cope that well. So what we can do for that is build a random forest on it. It scales way better to mixed and conditional hyperparameter spaces. It is a little faster as well. But you have, instead of a Gaussian model, you just have to build as a surrogate model, you have to build a random forest on all the observations you have. Or you can try a Bayesian neural network. I'm not going too far, too much farther. What basically it does is that the random forest, it will not look like a smooth line here with nice Gaussians overlaid. It will be more edgy. It will look like a tree structure there. So more stepwise function in the end. Or if you build a lot of trees, it will look more and more continuous. But you're basically trying different models to find here the straight line and its uncertainty. Bayesian neural network is also there. It's very flexible, very scalable, but it's based on its complexity. It's usually only worth the effort for huge problems like automated statistician or cache. What is cache? Is basically like you don't only decide on the hyperparameters, but you also going to decide on which algorithm to use. You can try a random forest, you can try an XGBoost, you can try a light GBM, you can even try a neural network. A cache problem also includes that in your optimization exercise. The best one so far is the tree parson estimator. So last but not least, and definitely most important, is a tree parson estimator, which basically builds your surrogate model by looking at very well performing and lowly performing trials, which is basically instead of a Gaussian model, you try to build a KDE, so a kernel density estimate, which is non-parametric, so it's not bound to any distribution, and you split it up between promising ones, very well performing. Usually you use a cutoff of about the 5th percentile of everything you already observed to find it like, okay, this is promising, this is good. And you build a different kernel density estimator for those who are below your threshold, which are actually bad or worse than what we already had. And it looks at a kernel density estimator of it, and the ratio of both is actually proportional to the expected improvement, which basically makes this a very attractive and a very quick algorithm. It's very quickly running because you don't have to decide you don't have to recompute for every observation you already made your expected improvement all over the parameter space. You can just use your kernel density estimates and quickly compute the ratio of both and pick the optimum. So it basically skips a step. It's non-parametric and it goes pretty fast. So those are our model-based algorithms. We basically almost checked all our boxes. We have a more efficient one. A more effective one, so we can find near optimal hyperparameters or even the optimal hyperparameters We learn from the past, so we learn from previous mistakes, but we still have to wait for it a while. That's where the hybrid models come in. So we have model free one, brute force, or we can use steroids. We have the smart one, model-based and smart algorithms for optimal results. What we're really looking for is, again, the combination of both, trying to combine the model-free brute force or steroids and put it in our smart algorithms, which gave rise to BOP. BOP is always our friend, which stands for Bayesian optimization on hyperband steroids. So you start with hyperband, so a random configuration, save all trial evaluations, and after you have done that a few times, you have enough trial observations to bring in the Bayesian optimization or with the TPE to start taking over future configuration selection. So basically you build a hyperband, so you select out some configurations, and for the next configurations, you use a Bayesian optimization technique to pick something in the neighborhood or to explore the rest of your parameter space. So it's basically both ways combined. You can prune less performing models, and you can swap out just a random pick for the next configuration with a more smart algorithm. So it balances exploitation and exploration. You use the model with the largest budget for exploitation, and you inflate the bandwidth of the multi-dimensional KDE. That's a very technical thing. So you basically explore using kernel density estimates. So you use a Bayesian approach for that, and you use the model with the largest budget, so the one that wasn't pruned, to exploit what you currently know about it. May seem quite technical, but it is a technique that works pretty well. Basically, what you can see, if you compare those, if you go for a BOP, it speeds up very much until it almost reaches normal Bayesian optimization, and then you see this curve, so it still speeds up because it can explore a lot more configurations, and it picks them in a smarter way. So you end up with still the best model so far. You have some others. You have multi-fidelity ensemble surrogate and hyperband steroids, which is basically using different optimization techniques, but those are very new and still need to prove their worth. So I'll just skip over this for time's sake, and I will go to the demo, which is basically I looked for you into Optuna, which is a hyperparameter framework. Hyperparameter tuning framework. I will pop this up. So I built for you, you can see my screen, I guess, just in a very small collab. I just used the California housing training data set just to show you how do you build a hyperparameter optimization tool. So I take in the data, I just use some standard scaling. I do some train test split, which was basically already done, but I take out the labels, and then we can go to Optuna. What does it do? It optimizes any objective function, so you don't only have to use this, or you can use this much more general to optimize any objective function. For us, it's the validation loss function. It takes a set of arguments, which is basically your hyperparameter trials, and you try to optimize them. So in Optuna, we create a study, and a study is basically, it consists of a set of trials, and a trial is basically just one sample from your hyperparameter space. You just try out some values for your hyperparameters. That's what consists of a trial. And within a study, you try multiple trials until you optimize your objective function. So that's what it does. It consists of 4 steps. So first, you need to define a function that trains a model and returns the validation score. Then you also have to define how your hyperparameter space looks like. So where do we want to search and to which values do we want to search? Then you create a study, which is very easy. And for this, you need to decide like in which direction are we going to minimize or maximize. It would be a very bad idea to minimize your R2 score or your R squared or your accuracy. So make sure that you set this in the right thing. You decide to use a certain sampler, which is your optimization techniques, one of the previously discussed ones. and a pruner, which is basically deciding on your steroids. How do you decide which trials to stop prematurely and not allocate too much budget to, or not try to look in a dead end? And then you optimize the thing with your worker function. How does it look like? Basically, your train evaluate function takes your training data, builds a model. Here I chose for the light GBM model. It evaluates the model, in which you can go very deep. You just build a metric from sklearn, or you compute it manually, or you use something built in the LGB. It doesn't matter, as long as you have a nice score on your validation set, and you return that score. Step 2, define your objective function, and that's what takes the trial argument. And a trial is basically, it's a random pick from these hyperparameters. You put them in a dictionary, and you can say like, okay, I want a learning rate. I use a trial suggest, and here you can use log uniform. You can use integers. You can use the uniform distribution. You can use a float. You can use even a categorical. It doesn't matter. You can just decide where to look. Like the log uniform for the learning rate looks between 0.01 and 0.5 learning rate, and it just builds a log uniform distribution on it as being the prior, and it looks for some values in here. For your max depth, you have, of course, an integer. I chose between 1 and 30 with steps of 1. Excuse me. Then your number of leaves between 2 and 100. I just randomly picked those just to show you it can go through a tremendous big grid. So if you have to check on a grid for all of these, it will take you a lot of time to compute that. So better use a better algorithm. And again, you use the train evaluate to just pick the parameters, make it into a trial. So just sample from it, train the model, yield or return the score, and return the score again. So just the repetition of your train evaluate function, which is called within step 2. Then you create a study where you can see I specified the direction, which is your minimization. You can get your sampler. And in this one, I just put a random sampler. You can choose for the grid sampler. You can use the CMAES sampler, so with the covariance matrix evolutionary strategy. You can use the TPE sampler, which is, by the way, the default by now. And then you can put your pruner, which is basically your steroids. Your steroids you can use or decide not to prune. You can use medium pruner. You can use successive halving pruner. You can use the hyperband pruner. So everything is available. You just have to call it right, and it will prune out less performing steps. And then you call your worker function, which is basically study, optimize, and you give it your objective function, so just a function, and the number of trials you want to try. And the number of trials is basically how many times are you going to pick a new set of hyperparameters? How many steps do you want to take before you say like, okay, we've tried enough. This is what is going to be our best one. I set this here to 200. First, let me show you can also do a grid search if you really want to stick to the old techniques. You can do a grid search. I just had to simplify this a lot. So I just took the learning rate as a float, max depth, number of leaves, just to try something out. The number of boosting rounds I fixed, the early stopping you can put here as well. And just I provide just a number, just an integer number, it will not change. It will not try to sample it. It will just stick to these things. You can also get your objective, which is basically the root mean squared error here I use. You can use everything here. Right? You can also use binary. You can use different metrics, whatever is available in the technique or in the model you want to build. For me, a light GBM, you can use here. And the verbose, I usually set to -0, just to make sure that all the text I get is not too big to read. Then you train, evaluate, return the score. Your search space, which is only necessary here for grid search. So here I introduced them in params, but I want to search only through this space. So I only want to learning rate a value of 0.01, 0.1, and 0.5. Same for the max depth, same for the number of leaves. So I have like 3 options here for 4, gives me in total 48 combinations. So you will see, even though I said like, okay, try this for 200 trials, I just used the grid sampler using the search space here. You can see I pre-ran this just to save time. It takes about 19 seconds and it only ran 48, because there is still a 0 here. You run 48 trials. So you tried every one of them. And if I use the grid search, I basically end up with a score of 0.4 with these hyperparameters. These are what I think are the best based on the grid search. If I want to make this a little more random, on the code, not much changes. This remains exactly the same. My objective function gets a lot more hyperparameters here, just to show you like how far can we go. We can really tweak every hyperparameter here. It will just decide for you automatically which ones to tweak. And here I use the random sampler. Doesn't take any arguments, so you can just use it out of the box, random sampler. And you can see now it will not prune anything because I didn't activate any pruner. It will run 200 trials for you, try out all different random samples out of your hyperparameter space. It took 2 minutes and 15 seconds, and I end up with a much better score. Like much better, it's all relative because this is just a toy example, of course. In many contexts that I've tried myself, I really ended up with a lot better techniques if I go to the more specialized Bayesian optimization. But anyway, even the random sampler outperforms grid sampler, which is a good sign. You can use CMAS just as a toy example. But now I activated the pruner. So basically what you do is in your objective function, you report your score. This can be any number. I just put it to 200. If you put 1, it also works. This is basically unimportant, unless if you want to map it throughout all different trials. Your trial should prune. Then you really prune something out if it's less performing. So I just use the default one, so the median sampler, and then you can see if I start running this, I will quickly go to the back. You can see it just pruned several trials because they're not performing well. So they're performing way worse or less than median of what we already had. And those are just immediately pruned. We will not search for them anymore, which basically in this one takes 4 minutes. And I end up with a little bit less than a random search. So I was a little bit disappointed by that, but let's look at the best one in class or the state of the art right now. Let's look at what Bob did. Bob also, as I said, it's a TPE sampler on steroids, and on which steroids? On hyperband steroids. So I both get my sampler to the TPE sampler, my pruner to the hyperband pruner. I have to make sure that I activate my pruning using this piece of code or this block of code. And then you can see it prunes out a lot of my different trials. It takes me also 4 minutes, but ends up with what we can see is still the best RMSE value. Of course, I have to say, like, this was not so impressive for this toy example because it's a very stylized example. In reality, or on the use cases I used it for to build my own models, the difference was much more sizable than this one. So give it a shot. It doesn't take that long, and it really gives you very quickly a very good search over your hyperparameter space and gives you much better results. Now, what is also good about the whole Optuna thing is that there's a lot of visualization built in this package. So you can export everything. You can use it to MLflow. You can push it to Neptune if you put the right callbacks. It can save everything, but also in a notebook, just if you're trying something out, it can visualize what you are doing and how to go forward. The first one is like the optimization history. You can see what is the best model. And you can see first, it prunes pretty quickly. You can see no values here because all those values are pruned if they perform way less. And you can see that over time, it converges nicely towards all different trials, are very close to our best value up till now. You can also plot the parameter importance. So here you can very easily see, like here was the bagging fraction that I tweaked was the most important or the most influential hyperparameter to tune for this one. The learning rate and feature fraction are already a lot less. Bagging frequency was totally unimportant, so it doesn't matter which value you choose for this. So this exercise can already tell you, okay, yeah, where to speed up the process even more, to which hyperparameters can I look and which one are basically unimportant for my model performance, for my final model performance. It gives you a nice overview to go further and build better models in the future. Same for the slice plot. You can see, like, okay, do the trials converge somewhere? Like the bagging fraction, it started off in earlier trials, like all over the place. And the more darker the color, the more later in the process, you pick those hyperparameters. So you can see that they go very nicely towards towards 1 here. For the bagging frequency, it's still all over the place. You can try whatever you like. It also doesn't matter so much. So you can see and track very nicely how your parameter evolves or how they are sampled. Same here as in Neptune AI or very many dashboards. You can plot these things as well. I personally don't find them that useful, especially if you have a lot of unpruned trials. This one gives you a nice black box, like literally everything is colored, so it doesn't help that much. So what I use mostly is just these and the best model and see how it converges. That's a very quick overview of what Optuna capabilities has. It has a lot more. You can find it in the documentation of Optuna. It's very accessibly written. It gives a lot of examples as well on how to do things, how to build in callbacks if you need them, how to integrate it with things like Neptune AI or MLflow or any dashboard you need or you might want to track how your models are being built and how you end up with the best hyperparameters. And that's basically where I end my demo. Thank you very much for listening. And back to Dorian.
Thank you, Hans. It was really interesting. I've got a few questions. Maybe first let's start with the dumb one. What does the word surrogate mean?
Well, basically, your true objective function, as I told, like you try every time you try a new hyperparameter setting or a new configuration, you have to retrain the model, which is hard. It takes a lot of time. So if you can replace it by a model that's much easier to evaluate and can still map your hyperparameter configurations to your objective function, you actually replace it by a different function to approximate it. And that's basically what a surrogate means. You build a model to try and do the mapping for you without you having to evaluate every single hyperparameter configuration.
So surrogate means replacing, basically.
Yeah.
Okay. Then another question I have is, like we've seen during the Bayesian optimization, that you have this acquisition function, which is a function that tries to balance exploitation and exploration. Do you know which class of functions are doing this this trade-off?
Yeah, usually what is most oftenly used is the expected improvement, as I told you, like here, this one. So you build on the uncertainty to get, the uncertainty shows you like where to explore more, because everything is uncertain and you can end up with exploration and looking away from the objective function. And you have your function. So basically here, at the straight line you have here to do exploitation. So you really look in the neighborhood, or your uncertainty is driven in the neighborhood of one of those previous evaluations. So this is just for expected improvement.
And how do you calculate it? Do you know?
Yeah, it is basically, I know how to calculate it, but I was not going to go into specific formulas. But it's basically an expectation of how much better the next result is going to be compared to the best result obtained so far. So basically what you do is, like, as I told, like here, you draw a line at the best evaluation you already have and look at everything of your uncertainty that goes below, and even of your objective function actually, that goes below this line. If you want to minimize loss, here on the y-axis there is loss. So you basically map this whole area of your uncertainty below it and choose the maximum of that, or actually the minimum in this case. Yeah, it's just mirrored. You choose the minimum value and you put your next hyperparameter configuration exactly there to see, okay, this is what I think gives me the best improvement. Evaluate that. So retrain the model, evaluate that. You end up with what is on your true, objective function, and then you can redo the thing, rebuild the surrogate model, which is now closer to the truth, and continue the process in the next iteration.
During the demo, so you still need to provide certain ranges for parameters. Do you have any advice for us to pick nice bounds, nice ranges?
Well, for that you can still, it's basically it's problem dependent. You can just throw everything at it. You have to think about, okay, where do I want to look, and which learning rate is, for example, is acceptable, even in the literature or previous models you built. But an additional thing is, like, you don't have to be restricted. You can go from very low learning rates to very high learning rates. Your optimization technique, you can really work model agnostic, is what it's called. You can really set this very broad, and your algorithm will very quickly choose a direction and say, like, okay, I'm not going towards those learning rates. I'm going to be restricted in this range. So you can put it as broad as you want. Of course, like for your lambda here, do not put it to 10,000, because that's probably that's highly likely to bring everything to zero of your parameters. So choose problem specific there.
Yeah, so it's still a little bit of choosing for us. We can do it all automatically.
Yeah, that's basically the strength of building such an algorithm. You don't have to use too much knowledge. You shouldn't be too over, or you shouldn't be overconfident, but you can use very broadly. Your algorithm will do the optimization for you.
I think also, like, the broader your ranges, of course, the longer the execution time.
Yes. Yeah.
All right. I don't have any more questions. Okay, then I thank you, Hans.
You're welcome.
Thank you, everyone, for watching as well. Stay tuned. There'll be other sessions coming on as well, and of course, also other tools. So I'll see you there, and have a great day.